I had.
Hi, can you hear me now?
I can hear you. How's it
Okay,
going?
super. Good. How about you?
Pretty good. It's a beautiful
Good.
day here in Calgary.
Is it?
Yeah, it's pretty nice.
We were about +2 or +3 yesterday, but it's gotten cold today and tomorrow it's getting warm again.
Oh, well, there you go. It can
So,
change every day, I guess. Yeah,
oh
we're,
man.
we're at like, I think plus 15 right now. So
Oh wow.
don't know how long that's going to last, but
Probably not very.
no, exactly.
I should try sharing my screen just to make sure that it's
Yeah,
working.
exactly. No, that'd be a great idea. Yeah, so the general thing, it's quite informal, and we have, I
Mhm.
think, 6 or 8 folks that have confirmed. We'll see who actually ends up coming. Um, do some introductions, and those introductions will ask folks about what they're up to, some of the
Yeah.
interesting things, and then get into your presentation. So looking
Okay, you
forward
see
to it.
my screen?
I do. Yeah, it looks great.
Okay.
Nice picture. Oh wow, that's cool.
Yeah. It's a lot of pipe in there.
Exactly. Wow. So how many like that? Why are there so many pipes? Where do those things all go?
Okay, there's a whole bunch of pipes coming out of the ground. These are drilled horizontally down to depths
Okay.
of about 24 and about 16 feet.
Okay.
Each of these is a pair of pipes that's about 500 feet long each direction. And then they'll be connected up to these bigger pipes, which take it up to a shipping container, which was installed about here.
Okay. Very cool. Wow. And so it's all up and running right now. Have they got
Yeah.
students in those residences too, or?
Yes. Yeah, they've got two of the buildings running. There's about 8 or 9 that will eventually be connected.
Wow.
And so yeah, the first two are running. The other ones they'll replace. They're going to be connect up 2 more next year in the next year or two.
Okay.
And then over the next 5 or 10 years, they'll connect up the rest of the buildings as you know, as the mechanical systems need replacing.
Sure. So, so you've done projects like this. Were you involved in the one at University of St. Boniface?
Yes.
Okay.
Yeah, they've got one building there, and
Yep.
that's been running since probably like 2008, 2009, thereabouts.
It's been quite a while.
Yeah,
I think they've had some issues around the recharging of the ground, or I actually don't know the details.
we're actually monitoring that system now. It looks like it's running pretty well right now.
Oh, good. Excellent.
We're doing a study for Efficiency Manitoba and we've got probably about a dozen or so systems that we're monitoring.
Okay. Oh, that's great to hear. Efficiency Manitoba has presented at our
Hmm.
meetings, and we
Yeah,
also work quite closely. Oh, there's Randy. We also have had worked with Manitoba Hydro. They've
yeah,
presented. So there is interest, in different projects potentially, and this is kind of technology that seems to have been you guys are innovating it quite a bit in Manitoba, and I think your company in particular, and proving that cold weather isn't isn't the and harsh climate isn't a huge obstacle. Do the buildings have to be kind of built at least to a little bit better standard, or?
not really. We can the size of the ground heat exchanger gets smaller if you've got a better
Yeah,
building.
yeah.
But we've done existing buildings. One of the buildings on the campus here, they did some fairly good upgrades on the building envelope and that. The other
Okay.
one, they didn't do much onto it, and both of them are working fine, connected to it.
That's great.
Hi,
Wow.
Randy.
Hello, everyone.
How
Hey,
are you
how's it
doing?
going?
Good, and you?
Good.
And sorry I missed our meeting. Was it last week? I'm not sure what happened. I have too many calendars, so thanks for calling me up to confirm. Really, have to apologize. It was terrible. So Randy, how are things? You're down. I guess you know. Is it Aaron you no longer have? Are you planning to replace or hire into that position, or?
Oh, Kara. Yeah,
Sure, yeah,
Kara's
Kara,
gone.
sorry.
Yeah, we've replaced that position. It's just a matter of now figuring out who can take that on or whatever. Yeah, it's a big learning curve for the people we would have right now. So I'm not sure,
Yeah,
yeah, where we're going with that one yet. But yeah, she was quite good at that and had a handle on it. And sorry to lose her for that. That's for sure, especially with all
yeah,
this with this happening, right?
exactly. Wow, kind of the timing was tough. Yeah,
Yeah,
well, you've gotten through it.
because of the
And
size we are, it's always hard to add on. Everybody's maxed out, and it's always hard to add on things to someone. And
yeah,
so we'll see.
it's something that's often a bit of a choice. If some, have maybe a passion for a little bit or
Exactly.
whatnot.
Yeah.
So
Hmm. Yeah, some jobs evolve by who's in it, right? Of
yeah,
what their interests are, and yeah,
It's a little harder in a smaller organization to meet the needs that are out there and to fill the needs when when you need them.
yeah, definitely.
Yeah,
Yeah.
you know, can't afford to overspend on people, and you can't afford to underspend either. So
No, but you always lean that way more than the other way.
yeah, it's just the way the nature of the beast, right?
Yep.
totally. Well, if there are ways I can help, I'm helping out at University College of the North in St. Boniface. I'll probably be coming through next little while to visit those folks. So if there's any ways I can help, let me know.
Okay.
We have had I've had acceptances from Assiniboine and University College of the North. And I actually heard, oh, and here folks are just coming in now. Here's Stephanie. So I think we'll have a pretty good show. And I actually heard from somebody this morning that is excited to hear more about this project. So did you have a pretty good you had that event where folks could come out and see the installation? Was there a pretty good turnout for that or?
Yeah, we've had a couple good turnouts
Oh, okay.
with a few groups. Yeah, the city, Red River, Sedona, that whole group that's putting up that that basically indigenous whole
Oh,
I don't
now we're
know
Dina. Yeah,
where,
okay.
yeah, Sydney, whatever they're setting up there. I'm not
Yeah.
sure. I haven't seen the whole plan, but they got the gas station up and they're building some other buildings now already, so it is on its way.
Oh,
So
okay.
they
Well, that's
came as
cool.
well, and that would
Yeah.
make a lot of sense for a group like that to have Geo there with all the buildings that are going up. It's kind of a urban reserve kind of thing, I think is kind of what they're building. I'm not sure.
Okay.
You know any more about that, Ed?
Yeah, they've got about it's the old Capyong Barracks, that old army base from way back when, and
Hmm.
they've got I think about 160 acres of land. Uh,
Yeah, it's a lot.
Oh,
it's a
okay.
lot, yeah. They got
Yeah.
about four, I think it's 4 or 5 blocks of land,
Yeah, it's
4 or 5
big.
city blocks, yeah. And yeah, they're building all kinds of apartments and townhouses. They're talking about a hockey arena, a few other things.
Okay.
Yeah.
Oh,
Yeah.
wow. Very nice.
Imagine a hockey rink, and that would work really well with Geo with other buildings because that's quite different.
It sure would, yeah. That
Yeah,
or data centers.
yeah,
They produce one heck of a lot of heat.
yeah,
Data center does.
yeah,
Okay.
exactly.
We're looking at one in Winnipeg where they're looking at about 100 megawatts of power. That's if it was all electric heat, that would be enough to heat about 10,000 homes.
Exactly. That's really significant.
It's a big chunk, yeah. And if you connect it
Wow.
to a ground loop, it could feed about 50,000 homes.
Okay.
Hmm.
So is it producing heat or is it actually producing electricity?
They use a lot of electricity to run the computers, and all of that heat has to go somewhere because they have to cool those computers, and so they have big chillers, and all of that comes out as heat. And usually
Yeah,
they just evaporate water to dump heat to the atmosphere. But if you can use it connected to a system like this, you can really take advantage of that.
exactly. And so you install systems across kind of North America? Is that
Yeah,
right?
we've done work. We're doing some projects in New York State right now, in Virginia.
Okay.
We've done projects in California, right across Canada.
Interesting.
We do a lot of work with engineering firms that really haven't had much experience doing ground source systems. Like that's
Exactly.
kind of our main client, our 70% of our clients probably are engineering firms.
Very good. Just looking, it's almost time. And thanks everybody who's joined us. I've got some confirmations of folks coming, but I think we might just get started and they'll join us as they expect to, as they make their way. So we can start with some introductions. Folks all know me. I'm Donald Jans, working out of Calgary, helping institutions across North America now advance campus and community sustainability. This nonprofit has got actual grant now, a few grants now, from one from Alberta Eco Trust, where we're installing some EV chargers in multi-unit residential to test out how that works, low and medium income. It's been a little bit slow take up, and there's some energy issues in the technology we have. It was developed at University of Alberta that we're implementing is specially kind of designed. It's got 4 or 5 patents to not just provide energy, but actually manage load. So you can go into situations where you may not be able to increase the capacity because of restrictions around what's available from a building or situation, and still be able to provide effective charging. So some of the work we're doing, and working closely now with a couple of institutions in Manitoba, University College of the North and St. Boniface. Doing some really exciting work, but also working in Sask Poly in Saskatchewan, folks across Alberta and BC, and having some good conversations with some institutions in the US as well. So I think we'll just do some rounds. Maybe Ed, you can kind of introduce yourself.
Sure. Yeah, I started the company. I've been working in the geothermal heat pump industry since the early 80s, longer than I care to admit sometimes. Learned a lot of ways that don't work over the years. And for the last probably 7 or 8 years, we've been doing a lot of work on thermal energy networks or district geothermal systems. And Canadian Mennonite University is one of the first ones that has adopted this system in Western Canada. It's basically, and that's what the presentation is about. Most of our clients are engineering firms that haven't had much background in geothermal system design, so we end up working across North America, sometimes internationally, and we've done work in Australia and in New Zealand, South Korea, number of places, and so we've been exposed to a lot of different types of systems in different places. Thermal energy networks are really being focused on. New York State is building probably about 4 or 5 systems like this right now. They're doing feasibility studies on several projects, and that's happening in Colorado and a number of other places as well. There are some district systems in Richmond, BC. There's one that's being built in at the old Air Force or airport in Edmonton, Blatchford.
Yeah.
And but it is and a lot of people are learning how to do this, and there's different ways of doing it. And what I'll be going through today is describing the system at the campus at Canadian Mennonite University. So maybe Randy is with the CMU, so maybe you want to introduce yourself.
Yeah, I'm Randy Neufeld, Director of Operations here at CMU, and I as well have to admit that I've been here since the early 80s as well. So it's been a while. I've seen a lot of changes here. So this is exciting, some of these new changes from what we used to have. And so, yeah, I've seen a lot happen here. So I'm looking forward to more happening. I'm not sure if I'll be around for some of those.
Setting them up for them, though. That's great. Richard.
Yes. Let me just, oh, okay, that's good. Yeah, so I'm Richard Frechette. I'm Vice President at the University of St. Boniface, Vice President of Finance and Administration, and yeah, and then we're just in the midst of getting our STARS report done. It's been taking a long time, but we're almost there, almost there.
Oh, exciting. Stephanie.
I'm Stephanie Fulford with the Sustainability Office at RFC Polytech. Congratulations on your progress on STARS. We just got ours submitted this fall as well. And yeah, it's a lot of work. We also had an opportunity to tour CMU this fall, so thank you guys very much for that. It was definitely spurred a lot of conversations. Everyone really, really appreciated the tour. And yeah, we're continuing to have some big conversations about energy at our Notre Dame campus in particular. So it'll be an interesting next few years for sure.
Excellent. Yeah, look forward to learning more about that. And yeah, congratulations on your performance on STARS. Not many institutions do as well as you do. So I really appreciate that leadership. It's fantastic. Sarah.
Hi, everyone. I'm Sarah Campbell. I'm the coordinator of sustainability here at Winnipeg. Yeah, congratulations to UC Boniface for STARS. We just got our STARS rating in December as well, and we're able to get our first gold. So that was good for our campus as well. And we are starting the conversation of our new sustainability strategy for our campus. So decarbonization, greenhouse gases will absolutely be in there. And so I'm looking forward to this presentation. Unfortunately, I missed the CMU tour, but if you're ever giving another one, you know, I'd be open and willing to come down. Thank you.
Absolutely. No, that's great. Thanks. And yeah, congratulations. I hadn't seen that you'd submitted recently. So the 3.0 that they've got for STARS now it's a little bit more streamlined, but it's a lot of work to convert and to understand how it all works. So yeah, I appreciate that work that you've done. So I think I'll turn it over to you, Ed. You can give your presentation. And I guess I have lots of questions. I'll try to hold them to the end. I think that lets you kind of get through, and you'll probably answer a lot of them as well. But yeah, looking forward to this. Thanks.
Okay, real quick description of what a ground source system is. So basically, the ground underneath us, depending on where you are in Winnipeg, it's going to be about 45 degrees Fahrenheit or about 7 degrees C. Southern California, it's going to be as high as 75 degrees Fahrenheit or about probably about 25 degrees C. It varies depending on the climate. And the big thing about using the earth as a heating and cooling source is that the temperature is pretty constant. Once you're down about 5 meters, 7 meters, 8 meters or so, the temperature of the ground is really very constant. It doesn't change a whole bunch. As you get near the surface, it does change with the outdoor air temperature, but you've got an insulating effect on that. So what we do with a ground source system, we build a heat exchanger in the ground, and typically that's made of plastic pipe, similar to the pipe that the gas company uses, and circulate fluid through that. As the fluid circulates through that, it becomes about the same temperature as the earth around it. So that fluid then circulates through a heat pump that's located in the building. The heat pump either cools that fluid and uses that heat that's taken from the fluid to heat the building or make hot water, or vice versa. It's taking heat from the building when you're cooling the building and rejects the heat to the ground. So what we're doing is changing the temperature of the earth around the pipes. And that's the big advantage, is that you've got a lot of mass that you're taking heat from or dumping heat into. It takes a lot of energy to change that. It also means that you need to know how much heat you need for heating the building, or how much cooling you need, how much heat you need to get rid of when you're cooling the building. So you also have to know what the capability of the soil is and rock that is to absorb that heat or to give up that heat. So there's a lot of calculations to that. It's not something that most engineering firms are used to doing. That's one thing our firm has focused on, is strictly on the ground heat exchanger design, but we need to know what's going on in the building to do our work properly. So what we're doing is changing the temperature of the earth. The gray areas are the outdoor air temperatures in Winnipeg on a typical year. What the green is showing what the ground temperature is doing when we're taking heat from it or dumping heat into it. So it gets as about high as about 80 or 85 degrees Fahrenheit, or about 25, 30 degrees C, and gets down about around freezing or just slightly below freezing, depending on what we're doing it and depending on the time of year. This is about the coldest time of year that you're going to see in the ground. About August, July, August is when it's going to be at its warmest. So what we're doing is basically taking heat from the building and dumping the heat into the ground. We're warming up a big mass of dirt in the summertime. And in the wintertime, we're extracting heat from the ground, putting it into the building. There's a lot of different ways of moving heat to and from the ground. In vertical boreholes is quite common, depending on how much land area you've got available. And they have, you can drill vertical boreholes up to, I think they're drilling them up to about 800 or 900 feet deep, or about, 300 meters or so almost in some areas. And depending on the geology, in some areas we don't drill much more than about 100 meters or 120 meters, but it really depends on the geology and what the drilling contractors in that area are available. If you've got a lot of space, we can excavate a large hole in the ground, put a bunch of pipe in it, fill it back in, and take the heat from that mass of dirt. And this might be only 7, 6, 7, 8, 9 feet deep. We've done a lot of schools where there's a lot of property exactly this way. You can also do horizontal directional drilling, which is what's used at the project at St. Boniface University at the nursing pavilion, and what was done at the Canadian Mennonite University. If you happen to be near a body of water, near the ocean or a lake or whatever, you can just lay a bunch of pipe in the lake. The water at the bottom of a lake is typically around about 39 degrees Fahrenheit. That's when the water is at its most dense, or about 4 degrees C. We can take heat from that or dump heat into it quite easily as well. Or you can also connect directly to well water if you've got a good aquifer on the site, and areas in Winnipeg do have very good aquifers. You can use that directly and circulate directly through that. So there's a lot of different ways that you can move heat to and from the dirt. What's happened in the last several years is there's larger buildings often have fairly deep piles. This is a project in New York City where they have piles that go down about 120 feet or about 35 meters, 35 or 40 meters. Put the pipe in there and then fill these with concrete, and you're touching a lot of dirt. Or if you're in a subway, put pipe in there, or in sewers, you can take heat and dump it into the sewer and the dirt surrounding the sewer. One of the problems in the industry is that the perceptions about the systems are that it can be very expensive to build, it can be risky, but the big deal is that you can really reduce carbon emissions. And because we're using electricity to run the system, and if you're in Manitoba, the electricity is fairly clean. We're not burning a lot of coal in Winnipeg, in Manitoba, or burning a lot of oil or anything like that to produce electricity, where it's mostly hydroelectric power. So the energy you're using is virtually CO2 emission free. But these are, I call them misperceptions. They don't have to be nearly as expensive as they're perceived to be. The problem is not a lot of engineering firms have a lot of experience designing systems, and tend to wear belts and a suspender and have somebody walking behind them holding up their pants as well. So so they end up costing more than they sometimes should. Bigger is not necessarily better. CMU has a fairly lengthy background in geothermal systems. This is a residence that they built about 2005. It's got vertical boreholes in the parking lot beside the building. It's been working quite well since it was installed. It will eventually be connected to the system as well, so we can take advantage of sharing energy from one building to the next. This is the building, another residence that is adjacent to that first one. This is Petker Hall. It's about 38,000 square feet or thereabouts. It was built in about 1958, and it was where the building itself has needed some fairly good upgrades for insulation and things like that. Windows were replaced a few years back, but the mechanical system needed a fairly major upgrade, ventilation system as well. So this is an opportune time to take a look at the existing building. And if you're looking at sustainability, then you can, this is an opportune time to do that. The old gas boiler was replaced by 2 heat pumps that produce hot and chilled water. And these are storage tanks that are part of the system, but this is connected to boreholes that are, we'll get into where the boreholes are located, but these are taking heat from the ground under the football field. That's about 500 feet away. So the other building that was done connected to the system as well is one end of the main administration classroom building. And this has a different kind of a system. It's got heat pumps that are tucked into the ceiling space. They produce warm air or cool air directly and provide heating and cooling directly. They're also connected to the same system. This is a look at the whole campus. This is the first building that I showed you, the Concord Hall. This is where the vertical boreholes are for that existing building that was built in about 2005. This is Petker Hall and the dining room associated with it that was renovated and converted to a geothermal system. This is the part of the building of the administration building, classroom building, that was also converted. The rest of the buildings have been left alone at this point, but will be connected at some point in the future. So Concord Hall, Petker Hall, and the north end of the administration building. This is the area where the horizontal boreholes are drilled, in this area, in the football field. And again, different ways of getting pipe in the ground. This is part of the thermal energy network. We call this an energy transfer pipe. All that it does is move energy around. Think of it as a conveyor belt that moves energy. It moves energy by circulating the liquid through that, and the buildings and ground heat exchangers are connected to it, either add energy to it or take energy away from it. So this is an animation of how a district energy system works, thermal energy network. So you can start out a system like this with just individual ground heat exchangers, which is similar to what Concord Hall had, an existing system that can be tied into the whole system. Then when you're ready to tie it in, well, then you can add other buildings to it at will, and basically add more ground heat exchangers to it, to the system, as you make building renovations. Add more systems, add more ground loops, add more buildings to it. So that's ultimately what it would look like. And you've got a conveyor belt going through the middle of it that moves energy from one building to another. One building might require heat, taking heat from that energy transfer pipe. The next building might be putting heat into it. And what that allows us to do is reduce the size and the cost of the ground heat exchanger that's connected to it, because you're recovering and recycling waste energy from one building and moving it to another. Then you can take it a step farther. You can add another module. If you've got, for example, CMU has a campus on either side of Grant Avenue. They could be linked up if it makes sense and if it's economically feasible to do it. If you happen to have an ice rink in one end of the campus, they produce a lot of heat that can be moved over to the far end of the system, and you can take advantage of that, or a data center, anything like that. So that's basically how a thermal energy network works. You can also add one thing that, because you're basically creating almost like a utility, you need to be able to make sure, like, for it not to work is not a good option. Especially in our climate, not being able to heat the buildings in the middle of January is not really a good option. So you have to be able to manage how the system is working, what the temperatures are in the different ground heat exchangers. And it becomes a bit more difficult simply because the way a building is used from one year to the next can change. Renovations made to the building will change heating and cooling loads, heating and cooling requirements. You change the windows, you change the loads. The weather is going to change from one year to the next, and that's going to change how much energy you need, how much heating you need, how much cooling you need. So you need to be able to manage that, and you can add things like things to get rid of excess heat. You could add snow melt on sidewalks, for example, if you got a lot of excess heat. You can dump heat to the atmosphere through a fluid cooler and dump heat in the winter. You can add heat to the system if you need to in a cold climate by using warm summer air in the summertime, and then basically manage the temperature, store the heat in the ground. For example, in my own house in Winnipeg, houses in Winnipeg tend to require a lot more heat than they require cooling. And after about 20 years of operation, the ground heat exchanger in my house dropped down to about 22 degrees Fahrenheit, or about -5 degrees C, which is colder than most heat pumps like to see. They become less efficient. So about 5 or 6 years ago, I added a solar thermal panel to dump heat into the ground heat exchanger, stored the heat in the ground in the summertime, and pull it out in January. When you apply that to CMU, basically what they've got right now, they've got these buildings. They've got a sea container over here. And this is what's connected to the system right now. Phase 1, the Petker Hall, and the north end of the administration building. And as more buildings are added, the ground heat exchanger is expanded. And this is about where they will plan on being in the next couple of years, connecting the Concord Hall up in the top left-hand corner, phase 2, and another apartment building to the system. They're going to need renovations in the next couple of years, and that's when they can be connected. And then as that moves along, other buildings, another future building is going to be added. This is the other south end of the administration building. And then eventually the Heritage Center. And then at some point in the future, it might be 5 or 10 years down the line, they can easily add another building on here and connect that to the system as well. And then expand the ground heat exchanger as the system grows. So it avoids the need to have to build the full infrastructure right up front. You can expand it at will. It becomes a modular system. You can add more ground heat exchangers. You can add more buildings to it at will, basically, as you have the budget to do it, as you have the need to renovate the buildings. So this is the way the ground heat exchanger was installed at CMU was horizontal directional drilling. They drilled, I think there's about 54 boreholes right now, got about 16 kilometers of pipe at 26 and 16 feet below the surface, or 5 to 8 meters for the first 2 buildings. Once all of the buildings are connected, they'll need about 40 kilometers of pipe under the ground, under the football field. And this allows you to do this with minimal excavation. It's less expensive in this area than vertical boreholes are. So this is the trend where all the pipes are coming together. There's 54 of these pipes buried under the football field. These will be connected to these larger diameter pipes, and this is where the sea container, which became the mechanical room, was installed. The pipes come up from underneath it. This was about last winter, about a year and a bit ago. Sea container is being dropped into place. That became the mechanical room. This is the inside of the sea container. This is the energy transfer pipe in this case. And then you've got connections to the ground heat exchangers and connections to the buildings. So I talked a little bit about monitoring. This is a 38,000 square foot classroom building in Winnipeg. You can see that the temperature got up to about 85 degrees is the highest the temperature got since last July, August, September. And then right now it's down at about 40, just around 50 degrees Fahrenheit. So it's actually above the normal ambient ground temperature in this area. That kind of indicates that there's more cooling going on in that building than there is heating, which is really not uncommon even in Winnipeg, where the temperatures do get very cold. There's a lot of heat. So there can be energy, like there's when the energy, here we're dumping heat into the ground. Here we're extracting heat from it. Here there's a bit of both going on. This is another building. This is about a 50,000 square foot office building in Winnipeg. There's times when there's heating going on and cooling going on. This is November, December, even in January, there's a bit of cooling going on. And this is a very good, about a 50,000 square foot office building. Again, it dropped down to about 50 degrees Fahrenheit, or just under about 45 or 50 degrees, and got up to about 85 degrees last summer. So if we see the temperature getting too high or too cold, then you've got a lot of advance warning. Because you're working with so much massive dirt, you can see well ahead of time. You can see that train coming a long ways away, and you can react or work to proactively address that potential problem. Heating cost comparison. These are the two buildings that are connected right now. These are what we anticipate the cost of running that building with heat with natural gas. It's about half of that with the electricity used to run the heat pumps. See the same thing in the North Administration Building, Catherine Friesen Apartments, and Concord Hall. Cooling load is reduced as well, about $3,500 to cool Petker Hall, about $2,000 with a geothermal system. And you see similar numbers in the other buildings. CO2 emissions are basically gone in this climate with the way the electricity is produced in Winnipeg, because it is very clean electricity. So basically, if the designers have done their work properly, you're going to get a good return on the investment, because we can reduce the size and the cost of the ground heat exchanger to accurately reflect what the building heating and cooling loads are. If you're monitoring it, you can manage the risk, avoid having any problems with it, and you can reduce the CO2 emissions. And it does work virtually anywhere in the world. We have done projects in all kinds of climates. I have done a project in Siberia in permafrost, where we're maintaining the permafrost under an aircraft hangar. And that heat that's coming out of the permafrost is partially heating the building. We also have done a project in Kerala, India, where the ambient ground temperature is about 82 degrees Fahrenheit, or about 30 degrees C. And you have to use different kinds of heat pumps for that kind of application because of the high temperatures, but you can make those things work. So that's basically a real quick description of what a geothermal system is, and what a thermal energy network is, and hopefully it describes how it works a little bit. I've got a fair bit of time for some questions. Any comments or anything like that?
Excellent. Thanks so much for the presentation. Really fascinating, and the scope of work that you're doing across the planet is amazing. So I'm sure there's lots of questions, and please, folks, if you have a question, please just pop in. One question off the bat is: has the cost of these systems changed over the years? Is it improving? Is it getting cheaper? Maybe new technologies are opening it up, or are we just becoming more aware of it and trying to do things differently? And so people are just using what's been there for a long time.
The cost of drilling in that has gone up in the last couple of years, simply because of labor costs and basically supply chain issues, and like a lot of things have gone up in cost in the last number of years. This is no different. Same with the heat pumps themselves. A lot of heating and cooling equipment has gone up in price, along with ground source. Where we can make the biggest difference is in the cost of the system is by accurately calculating what the heating and cooling requirements are of a building, and then sizing the system appropriately for that. And then we can manage the risk with that the operation of it, making sure that they continue working the way they should be, by monitoring the system and then proactively managing it.
Because I would assume that major costs, like you see, the operating costs are very low.
Yeah.
Where it has higher costs, and you can see that from the construction and whatnot, is the implementation. So if you can size that properly, you just limit how big it will have to be in the future. And is that kind of the major way then that?
Yeah, we did one study recently on a project in Winnipeg on about 165 acres of land where there's about a development of about 38 buildings is planned. A lot of multifamily residential, anywhere between 4 and 10, 15-story apartment blocks. A bit of a shopping area with grocery stores and drug stores and restaurants, and some office warehouse space. So 38 buildings in total, about roughly 8 or 9 million square feet of building. And the system that was designed for that, if it was amortized, built, and the cost was amortized over 60 years, similar to what a gas pipeline is, it's very, very competitive with that, if somebody is building the infrastructure.
So that's one of the things. It does last for a very long time. You'd expect a system like CMU's, the pipes and whatnot, to last 60 years. Is that right?
The system that they have at Concord Hall has been in there about 20 years. System in my house has been in since 1991. I replaced the heat pump in my house after about 23 or 24 years of operation, and just replaced the heat pump, connected it to the same ground heat exchanger. And that's what CMU could do as well.
Excellent. In the future, I understand that there's some plans to expand the system at CMU. The current system, as I understand, has been funded largely by. Is there a loan from? Was it the from I guess lower cost sources? Has that been the case? And also some fundraising, but. How has it been funded? And in the future, would you need to have access to lower interest rates, like I think you've gotten from a CIB or from other financial institutions? Is that going to have to be dealt with at the time, I guess, when it happens, to see if there's better financing available? Or
Randy could probably answer that better than I can.
Yeah, we basically got a loan for a little less than half of the cost, and the other half plus was done by donations. And with that whole, basically for the donation end of it, it's gone really well, and basically over exceeded what they had hoped to get and stuff. So yeah, they're shortening obviously the loan then for the amount of years that we'll need to have that. So that's worked out really well so far.
Excellent. And is the loan just a kind of a standard commercial loan, or is there some reduced?
Yeah, just through a credit union.
Oh, okay.
Here, yeah.
Interesting. And they had no problem. And why should they? But it was pretty straightforward. Okay.
Yeah, we've worked with them for years, and so that was not an issue.
Oh, excellent. So I wonder if in some systems, I think there is a possibility of accessing CIB funding, and it might depend on the scale. Yeah, they require pretty huge amounts to go ahead with it. But so
there are companies, just out of interest, that are providing financing in a couple of different ways. Some of them sell energy as a service, where they would design, build, own, operate, and manage the whole system, just like a utility. They can also do straight off-the-shelf financing of systems like that over 20, 30, 40 years kind of thing.
So your firm, GeoOptimise, worked with other engineering firm to install this system, or do you guys?
Yeah, we normally don't get very involved in the mechanical system inside the building, because there's a lot of engineering firms that can do that probably better than we can. We like to have some input into that, because what they do inside the building makes a difference on how well the system is going to work.
Yeah.
We basically do all the engineering that's needed for the ground heat exchanger, do the testing for the ground, do the design of the piping system and pumping system for the ground heat exchanger.
So that's interesting. We've had a few presentations from institutions that have done really significant upgrade of their systems. They've all used some sort of decentralized energy and heating buildings from a central source. One of them was quite interesting. Creative Energy at Thompson River University. They're not doing geothermal, but they're doing heat pumps, and that's exactly their model. Is they do kind of energy as a service.
Yeah.
They become your utility. They can access lower finance funding, and apply it across many projects that helps them reduce the costs. And so I'm curious, have you heard of Creative Energy? Are you familiar?
Yes.
Okay.
We
Would you
we have
work
done a
with
bit of
them?
work. We have done a bit of work with him in the past. We are working with a couple of other people that fund these systems one way or another. We can work directly with the client, and in this case, we work directly with CMU.
Yeah.
And then basically, as part of a team, there was a mechanical engineer on the building side, mechanical contractor on the installation side, a ground heat exchanger contractor that did the pipe in the dirt, and a controls contractor.
Okay, so that's really good to know that you work kind of and could work with them in a variety of ways. They've presented to their group the Thompson River presentation, and we've done a case study on Thompson River, and they're, you know, they seem to be able to work with geothermal, but you know, your expertise in the area, I could totally understand that could just help them be really effective. So,
Like a lot of potential building owners and a lot of engineering firms are hesitant to do geothermal
yeah,
because they're working with stuff that they're not used to working with. It's kind of a cross between civil engineering and mechanical engineering, and that's not something that's very well taught at the universities. It is starting to become more. We're developing some courses for a couple of universities as well, and we've done a bit of work with MIT to develop a course on district energy systems like this, and so there is more interest. It's just taking time to develop that.
Yeah. We had some conversations. I had conversations with the University of Calgary, who had gone through a complete engineering study and decided that the best cost way of meeting their really ambitious goals of eliminating natural gas basically from heating their buildings by 2035 would have been a geothermal system. And they mapped it out. There was 300 boreholes on one side of campus. Some of the biggest costs, though, would be converting all their existing buildings to low temperature water rather than steam. And it was going to cost them $1 billion. And at this point, I think they're kind of on hold. But it was very interesting to hear. And you know, I can totally understand that somebody with the actual on the ground expertise and experience might be able to look at that and make it more efficient.
We did a couple of studies for an electric utility in Minnesota in the last couple of years for 3 university campuses, small university campuses, about 25 buildings each. And one is Bemidji State University, and there we ended up working directly with the facilities managers who's running the systems that are there. They had an existing gas boiler system, central gas boiler and central chiller system, which is fairly common. And the approach that we took there was, and in Minnesota, they just like probably most universities, nobody's got the budget to do a wholesale changeover.
Yeah.
It's really expensive. So we ended up mapping out which buildings needed renovations either on their building or their mechanical system first. Started out by looking at designing a ground heat exchanger for an individual building, a couple of different buildings on different ends of the campus. And then here's how we can connect them up. Here's the next building that's going to be renovated. This might be like every year. Like if they got 25 buildings, they're going to need some upgrades on 1 or 2 buildings every year or every couple of years. And that's the opportune time. There's no point in throwing away a perfectly good system when you don't have to. And you can we basically tried to build a roadmap how they could get to net zero carbon by 2050.
Okay, no, that totally makes sense. And then, you know, the cost of the kind of central system, as I understand it, CMU, it's kind of overbuilt maybe slightly to allow you to easily connect up a couple buildings, but then at some point you'd expect to expand the underground system.
Yeah, ultimately there's going to be about 132 boreholes is what we're estimating at this point.
Okay.
But as we go along, because we're monitoring the system, we'll be able to see if we may have over-designed the first couple buildings, the ground loop for the first couple buildings. And then when the third building or fourth building is connected, we may not have to install as many boreholes as we had originally estimated. So we can basically right size it. By the time we're 5 or 6 or 7 buildings into it, we're going to be fairly right sized.
Excellent.
And
Did anybody else have other, go ahead.
Yeah, go ahead.
Did anybody else have other questions? Richard, you guys have some experience with your geothermal. I don't know if other institutions do as well. Did you have any specific questions or?
Well, one question I had was, I guess the heat that you're taking from in the summer gets stored in the ground.
Yep.
And does that heat kind of dissipate over time or kind of stays
Yeah,
in that area?
yeah,
And what's the efficiency of bringing that back in, you know?
the ground is really not doesn't really conduct heat very well. Gold or silver or copper and that conducts heat a lot more readily than gravel or sand or rock. So heat that we shove down there and put into the ground through the pipes basically stays around the pipes. It'll eventually dissipate, but it'll be around there several months. And so the heat that we're putting into the ground in the summertime, by when we're cooling the building, that heat is going into the ground, it warms up the ground, and then come fall, wintertime, we can pull that heat out again. We're not going to recapture all of it, but we're going to recapture a good part of it.
And I guess using the solar panels also helps to generate.
Yep, exactly.
But how does the solar panel heat the ground?
In my home, I've got a heat exchanger, a liquid to liquid heat exchanger that is connected to the liquid that circulates through the solar panel, connects it to the liquid that circulates through the ground heat exchanger.
Okay.
And during the summer, as the sun warms it up, as soon as it snows off of the off the solar panels in probably about mid-April or so, I can start dumping heat into the ground, and it'll dump heat into the ground till about mid-October, end of October.
So it's liquid going through those solar panels that gets heated up, just exactly. Like a normal pool.
Just like that's exactly what it is. It's an 8 by 12 foot pool heater.
Okay.
And for a bigger building, you'd certainly want a bit more.
Yeah.
But that one monitoring system that I showed was at your system at the nursing pavilion, I think it is.
Yeah.
And it's actually does more cooling over the year than it does heating, which doesn't surprise me. It's a good building.
Yeah, it seems like doesn't keep pace in the wintertime.
No? Okay.
That's what I've heard, but I'm not the one in charge of that. So
okay.
I think maybe this idea of solar panels might be interesting for us.
Yep. But yeah, we have like it's like we're monitoring it, and maybe by the end of the monitoring system, that we'll maybe have some better answers for you at that point.
Yeah. Okay.
That sounds very valuable. I'm interested, like metering has become so much more important because it's become easier to put meters in, everywhere to manage, see how much energy we're using, electricity, water, all these things. So is it typical that you would put meters in when you install these systems now so you can monitor the ground and how it's warming and cooling?
The industry hasn't been very good at doing that. We've developed, worked with a couple of folks to develop a system that will monitor these things. What it is basically is an energy meter that measures how many BTUs are going into the ground and how many are coming out.
Okay.
And with that information, we can compare that to what the calculated heating and cooling loads were. And we can also predict what the temperature of that ground heat exchanger will be over the next year, the next 5 years, the next 10 years. By seeing how it's going to react. And then you still have to take into consideration that maybe you're using the building differently next year than we did this year. Or maybe the weather is going to change from one year to the next, and that's going to change how much heating and cooling you do. So if you keep track of that, and you can adjust the way the system operates based on what you're monitoring.
Makes sense. Richard, go ahead.
I have another question.
Yeah, please.
Like a sewer water that's going through the pipes, is there any way to capture some of that heat energy?
There are a couple different companies that have developed heat exchangers that you can run the liquid from the sewer water through it and recapture that heat. There's ways of, if you've got a large sewer pipe going through the property, you can put pipes around the pipe in the sewer pipe. But yeah, there's different kinds of heat exchangers that can be used for that. It's not necessarily always cost effective to do that. It would have to do a study on that. In some cases it is, some cases it isn't. Depends on how much sewer water is going through that. If you've got a large residence, might be 500, 400 or 500 apartments or something like that, then you'd probably have enough energy available in the sewer water, enough regular use going through with sewer water going through there a lot of the time that you could make good use of it. And if it's a smaller system, it might not be cost effective.
Okay.
Richard, are you still having a bit of conversations with the hospital and the nursing home close by to work together?
No, we haven't done that. We're busy
Other
on other
things.
stuff, like the
Exactly.
STARS report.
Exactly. Well, that's totally fair. Stephanie or Sarah, do you have experience on your campuses with geothermal at all? I think that Red River may have some.
Yeah, we have a couple geothermal systems, and they are both groundwater source. And it seems we're, to be honest, we're not totally sure how efficiently they're performing. I think there's been some neglected maintenance, and so there's some issues with flow rates and whatnot. And so, that said, we are still interested in potentially putting in more geothermal down the road. But partially because of our experience with some challenges with the groundwater source, we are possibly more interested in a system more similar to what CMU has.
Okay. That's
Yeah,
interesting.
so the design and ensuring that the maintenance from like the people on the ground is a really important piece of making sure they're performing properly.
Well, and they're different, I can imagine, from an operational perspective. So folks may not be as familiar, and it just creates different challenges. But yeah, the water source and ground source and different approaches, I'm sure, can make a difference. I wonder if there's potential to do similar things to what you're doing on some other campuses, doing a study with Efficiency Manitoba or even Manitoba Hydro to evaluate the performance and then try to make improvements. I don't know if there's opportunities that way, but
Idea.
yeah. Sarah, does University of Winnipeg have any experience with this technology or systems?
We have a very small portion of geothermal under our McFeeters Hall residence, which only heats and cools like the common areas of our building. But we are looking at earth energy systems going forward. Yeah.
Okay. No, excellent. Yeah, there does seem to be expertise in Manitoba and Winnipeg, particularly with GeoOptimize, but I think just there's quite a bit of experience around. So it's nice to be able to take advantage of that. Is there, I wonder if there's any researchers, do you work with researchers directly at all or aware maybe of things going on in Manitoba, but maybe elsewhere that?
Yeah, we did a study in conjunction with Efficiency Manitoba. We're working on it right now on what is often called energy foundations, looking at there's helical piles that are screwed into the ground. They can pipe can be installed in those. We've got a couple of houses that we've done that with, and that's enough to heat and cool those houses. They're about 2,800 square foot houses.
Oh, wow.
And they've got enough piles under them to be able to do the heating and cooling. And that's going to vary a little bit. We have done an energy foundation system on a 250,000 square foot building in Manhattan, where there's 120 piles 120 piles that are 120 feet deep. And that does about 40 or 50% of the heating and about 30% of the cooling.
Wow. Interesting. So many interesting applications. Well, if anybody doesn't have any other questions, I think we are getting, we're at about time here. It often works that way. I'm so grateful for you being able to present and for the work you guys are doing at CMU. It's really been interesting. We've recorded this, and I'm glad we have. There's a lot of information in this, and I'll be forwarding it so folks can access it. Ed, would you be able to provide your slides? There may be folks who didn't attend that might be interested in that. That'd be great if you can send those to me. And yeah, no, I appreciate everybody's time and the great work that you guys are doing. Really appreciate it.
Yep. Okay.
Thanks, everybody.
Thank you, guys.
Yeah. Have a great day.
Thank you.